Hello class, this is chapter 1.5, and for this video we are going to work through a mixing problem example that has constant V volume. So let's look at the problem. We have a water tank that contains 1 liter of distilled water mixed with 10 grams of salt. So a solution is pumped into the tank that has salt concentration of 500 grams per liter at a rate of 0.1 liters per second. Let's just draw a picture here to guide us through this example. So we have a little tank, and the tank has 1 liter of water plus 10 grams of salt. Okay, and we pump a solution into the tank that has salt concentration, so 0.1 liters per second at the concentration 500 grams per liter, and we assume that everything is uniformly mixed, of course. Water flows out of the tank at the rate of 0.1 liters per second, and we want to calculate the amount of salt in the tank after 1 minute or after 60 seconds. Okay, and let's write down the equation. So you may recall we want to think about the change in the amount of salt in the tank with respect to time, and we do know a bit about that. So we know that we're pumping in 0.1 liters of solution that has 500 grams per liter. So that's going to be how much salt is coming in the tank in 1 second, and the salt that's coming out is going to be 0.1 liters per second of mixture in the tank, and the mixture is just going to be the amount of salt in the tank over the volume of liquid in the tank. So one nice thing to do here is that when we write down this differential equation is to check whether our differential equation is plausible by checking the units. So dx dt is just going to be how many grams of salt per second. That's the change of the amount of grams of salt in a second. And we can write this down as 0.1. 0.1 is going to be in liters per second. That's the amount of solution coming in. The 500 is going to be grams per liter. Okay, and this means that what this first term is going to be a number in grams per second, which is what we want, and that's good. That's correct. And this is 0.1, which is going to be liters per second. X is going to be in grams. The volume is going to be in liters, of course. This cancel out, and we have grams per second for the second term as well. So indeed, our units here check out, so which means that this is a plausible differential equation. Oh, before we move forward, let me erase this. Before we move forward, let's just talk about the volume a little bit. Now we note we have 0.1 liters of solution coming in per second and 0.1 liters of water coming out, and that's every second. And this implies that volume is constant. That is, it's always going to be what we started with, 1 liter of water. It's always going to be 1 liter, right? Because the amount of solution coming in and coming out in liters is the same. And this is nice because it enables us to write down our differential equation like so. X, and the volume is just going to be 1, so you don't have to worry about that. Alright, so this is going to be a differential equation we can solve by integrating factors. So let's move everything to the left. It's going to be dx dt. I mean all the x terms to the left. This is going to be plus 0.1 x equals 50. Alright, and this is a problem that we can solve by integrating factors. So we multiply both sides by the integrating factor. So remember that we care about the coefficient of the x term here. So it's going to be e raised to the n derivative 0.1. Okay, and that means that our differential equation is going to be dx dt times e raised to the 0.1 dt plus 0.1 x e 0.1 dt equals 50 e 0.1 dt. Alright, so it's the whole point of integrating factors is that we can write down this left-hand side in the form of a product rule, and that product rule is going to be x e 0.1 dt prime equals, so the right-hand side stays the same. Okay, and we can integrate both sides, and that cancels out the derivative term. We have an antiderivative over here. Okay, now it's time to solve for the integrating factor. So 0.1 dt is going to be 0.1 t, and so our integrating factor e raised to the 0.1 dt is just going to be e raised to the 0.1 t. Okay, and what follows is that we can rewrite our differential equation as x e 0.1 t equals 50 times e 0.1 t dt. Oh, remember that we didn't have to worry about the plus c when integrating the integrating factor term. Alright, so this is our differential equation. So let's integrate this right hand side. This is going to be 50 e 0.1 t over 0.1 plus c, okay, which leaves us with x equals 500 plus c e raised to the minus 0.1 t when we divide everything by e 0.1 t. Okay, and this is going to be our general solution. So again, we have to solve for the specific solution using initial values, and we don't really have initial values. Yeah, we do. Okay, a solution is pumped, so the tank starts with 1 liter of distilled water with 10 grams of salt. Okay, so that means that when t equals 0, x is going to be equal to 10, right? And this leads us to 10 equals 500 plus c. So 0.10 is going to be e to the 0, which is going to be 1. So c times 1 is c. And that leads us to c equals 490. And we can solve our differential equation by x equals 500, and plugging in the c into the general solution, we get 490 Oops, sorry. This should be a minus 490, of course. Whoops. Minus 490 E minus 0.1 T. Alright.